All right. Welcome to your third lecture on mathematical methods. Last time we found the first principles method. Okay. This was the first principles method. And we used it to find the instantaneous rate of change of a function at a singular point. Okay. That was the aim, and we got there pretty simply. No worries at all. Okay. In this lecture, we're gonna make it a bit more rigorous, and we're gonna almost try and reduce our efforts. Okay, what I'm talking about will be very clear once we start. So first of all, okay, let's start with looking at what we did last time. Last time we started at 2, 4, okay, and we ended at 2 plus h, f of 2 plus h. Okay, but what if I want to find the slope at 3, okay, slope at 4, slope at 1.5, okay? What if I want to find the instantaneous rates of change at those points? Would I have to do the whole thing again? Well, maybe not. Maybe instead of doing the process again and again for every number, we are going to just use x and f of x, okay, where x is any number that fits that is in the domain of the function. Okay, with that, we're gonna, because we're doing it with every possible number that we can do, we won't have to do this many times. You would hopefully end up with a formula that works. So let's try that. Okay, let's go. So we have x comma f of x, okay, and then x plus h comma f of x plus h. Okay, again, m is equal to the limit as h approaches 0 of f of x plus h. Take f of x over x plus h. Take x. Again, the x's cancel out, and you're left with this. Now, before we keep going, I would like to point out that this is first principles in all of its glory. This is the most basic form of first principles. Whenever you're asked to apply it, this is what should come into your mind. Okay? F of x plus h, take f of x all over h. Okay? This is where you should always start. Let's keep going. We know that our function is still f of x squared. Okay? Which makes this part x squared plus 2xh plus h squared. Take x squared all over h. Again, the x's cancel out. Cancel. And you're left with this. Again, you can factor out the h's here and here. And you're left with this. Now, again, important to mention that you can cancel these out because h is approaching 0 and is not actually at 0. Okay? You have to mention this here. Otherwise, it's possible to lose a mark, although I don't see that is necessary. But some teachers are stingy and you might lose a mark for this. But it's just better to make things clear. And then we say let h equal 0, and you are left with 2x. Okay, so now we know that for our function f of x equals x squared, the instantaneous rate of change, or the slope of the tangent, is 2x for any given x. Okay, so now we don't have to do that whole process over and over again. Great. Now, whenever you see this, okay, like you would have noticed that to get to my point, it took me a while. Okay, I had to say the instantaneous rate of change or the slope of the tangent line. Okay, instead of saying all that, I can say that this number here, it is the derivative of x squared at any x. Okay, at any x. So I don't have to mention all of that. And this means the instantaneous rate of change or the tangent or the slope of the tangent line. Okay, both of those things. This is what derivative refers to. Okay, so now that we know what a derivative is, we should also know how to show it. Okay, like when I talk to you, I can say this is a derivative. But here, when I write something down, I need to have proper notation. Okay, we denote derivative with this. Okay, this sort of notation. Now, let's just break down what each of these things are. This reads the derivative of y. So the derivative of this value here, so the derivative of y, this d reads with respect to x, okay, whatever value this is here, okay? So it reads the derivative of y with respect to x, okay? So remember, going back to our rate of change definition, okay? Remember how we said that we need to have two quantities that are related, okay? A quantity changes compared to some other quantity. It's the same thing happening here, okay? Something is changing with respect to another quantity, okay? Now, if I had, for example, dz on d theta, okay? This would simply read the derivative of z with respect to theta, okay? Simple. All right. Another way to denote a derivative is this simple notation. Sorry, the theta's stuck in my mind. Okay. That's a horrible looking x. Okay, good stuff. So this is another way to denote derivative. So when you have your function f of x, this is the derivative of f of x. Okay, f dash of x, that's how you pronounce it. Okay, same thing, same meaning, doesn't matter. If you are confused as to which of these you should choose, okay, to denote it, it depends on how the question is given to you. Okay, so if the question is given as y equals da da da, you would write your derivative like this, dy on dx. If your question is given in f of x equals da da da, you would use f dash of x. Okay, so it's important to just make sure you use the right notation. Okay, and that's it. There's no more worry to it. Okay. Now, my teacher always used to say that mathematicians are accurate but lazy. Okay, so when they came along with derivatives and all of that, they thought that, well, we can do x squared. Okay, we can maybe do x cubed. All right? Can we? Well, let's see. Can we? I want you to have a crack at that. Okay, find the derivative of x cubed. See how you go with that, and yeah, I'll meet you on the other side. Okay, so I hope you had a crack at it. Okay, I hope you gave it a good shot, and I hope you found that the derivative of x cubed, okay, so let's just say y equals x cubed, the derivative is equal to 3x squared. If you did not get that, don't worry, I'm just going to go through it right now, really quickly. So if y equals x cubed, okay, so dy on dx is equal to the limit as h approaches 0 of f of x plus h. Take f of x all over h, okay? Limit as h approaches 0 of x cubed plus 3x squared h plus 3hx xh squared plus h cubed take x cubed, not h cubed. No. Okay, cool. All of that divided by h. You cancel out the x's and you're good to go. Factor out the h, cancel out the h. Same old. Okay. Cancel them as h is not equal to 0. Okay, and then you go let h equals 0 and you get 3x squared. Okay, because the other values have a h and they become 0. Alright. dy on dx is equal to 3x squared. Like I said, that is the derivative. And hopefully we got that. Simple enough. If you have any questions, do put it down in the forum or ask a mentor. Okay, so make sure you get this covered. But yeah, so let's do one more. Okay, let's now try y is equal to x to the power of a half. Let's mix things up. Let's not try a full power. Okay, and let's try to find the derivative of that. Now this is a bit of a tricky one, but an important one. And once we do this one, it's going to lead us to a very important conclusion. So let's give that a try. Okay, so y is equal to x squared, so x to the power of 1 over 2. So dy on dx is equal to, again, yep, don't even need to read it out this time. It should be getting stuck in your memory at this point. Okay. Yep, x plus h to the power of 1 over 2 take x to the power of 1 over 2 all over h. Okay. Now, we can't expand it like we've been doing this whole time. All right. We cannot do that. Instead, what we can do is, first of all, rewrite this and then use something that I personally used to hate when I learned this, is the conjugate. I'm sure you've heard of it before. And we always use this when we are dealing with square roots and stuff. So we're going to use a conjugate and you're going to see exactly how. Limit as h approaches 0 of x plus h take square root x all over h. And the way we use a conjugate is by timesing this whole thing by x plus h plus root x all over square root x plus h plus root x. Now, why does this work? Is because here we are really just dividing one thing by the same thing. So we're really just multiplying by 1. Okay? So that is literally the same thing. And this whole thing just equals 1. Okay? So we're not changing what we have here. In fact, we just manipulated a little bit. Okay? So the benefit of doing that is now, if you notice that this is this and this are now in the form a take b times a plus b. Okay, and you can see how that's useful because that gives you a squared take b squared. Okay, that's the trick. And now using that, you get rid of the square roots, at least on the numerator. Okay, so like I said, that would be a squared take b squared. So x plus h take x all over h times whatever's here on the bottom. Okay, just not like that. Okay, let's fix my x here. Okay, so that is what you are left with. Again, the x's cancel out, and you are left with an h on the top. So I think you would have realized by now that if there is not an h that is either by itself or factorizable on the top and the bottom, so you can cancel them out. If that situation is not there, either you have not completed the process yet or you've done something wrong. Okay? In this case we do, so we can cut them out and say that as h is not equal to 0. And we can move on. And we're left with 1 over x plus h plus square root x. Okay. Now, again, having h as 0 has no issues. So that leaves us with, let h equal 0. And then that leaves us with 1 over square root x plus square root x. Okay, I should write that better now. 1 over square root x plus square root x, which gives us 1 over 2 square root x. That is your dy on dx. Okay, so let's just add that in here. Equal to 1 over 2 square root x. Or I can write that as this, right? After collecting all that information, that is all we're going to do for this lecture. In the next lecture, we're going to turn this information into a conjecture, and we're going to find a simple rule that is going to help us reduce all our efforts with the first principle. All right.